Hello, so today I'm going to be going over a AP Calculus BC problem in which you're going to be given two polar equations, r equals 2 and r squared equals 8 cosine 2 theta. And you're going to have to find the area of the indicated region. And in this case, the indicated region is going to be inside the graph of r squared equals 8 cosine 2 theta, which is called a lemniscate, and outside the graph of r equals 2. So let's graph those. And for a problem like this, we're actually going to be allowed the usage of our calculator, and I'm going to be using a TI-84. So we have our y and x, and I'm going to be trying my best to graph this. So on the TI-84, you can go to graph entry, polar, type in 2. And for r equals 2, the graph is going to look like this. So it's just a magnitude 2. So we know that it's literally just going to be the unit circle, except instead of a radius of 1, it's going to be a radius of 2. Right? So that's going to look something like that. And then for the graph of 8 cosine 2 theta, it's going to look something like this. Right, so like you can think of it as an infinity sign with these areas outside of the circle. So we're going to be looking inside the lemniscate, the infinity sign, and outside the circle. So that's going to be these regions right here that I'm going to be shading. And for a problem like this, it can actually be pretty tricky to figure out. Hold on. Okay. And it took me quite some time. I was trying to figure out if I can find, if I can find the area of one of these full things of the lemniscate and subtract it by the area of just the inside region of it, then I can find, this portion. But there doesn't seem to be any way to just find the region of this, because these are polar equations, so you can't treat them like a normal integral and just, if this is a normal, if these were just normal equations, then we could treat them, using just, it's a basic integral equation. But in this case, it's a little different. So what we have to do is we actually have to find the intersection points of these two right here. Once we find where these intersect, we can actually isolate this area and then just multiply it by 2 to get, to account for both sides. So in order to do that, we can treat r as 2 and simply plug in r to this equation. That's actually just setting them equal to each other, right? And if you wanted to think about it like how you would normally just set r equal to each other, this equation here is the same thing as this. So if we set r equal to each other, 2 equals plus or minus square root 8 cosine 2 theta. Alright, so then you square both sides, and then you're left with 4 equals 8 cosine 2 theta, and cosine 2 theta equals 1/2. And where does cosine equal 1/2? Well, we know that the inside has to be pi over 3. And, well, let's look at a unit circle real quick just so we can envisage this. So at pi over 3, the coordinate at the unit circle is going to be 1/2 square root 3 over 2, right? And if we're looking at positive x, then it's going to be 5 pi over 3 is going to be the other one. And the point is going to be 1/2, except it's just going to be negative square root 3 over 2, right? Because we're in the negative, we're quadrant 4, where y is negative. So it's going to be 2 theta equals 5 pi over 3. So theta, so the angle from the origin is what we have to find, right? Because these are this is a polar equation, so we're not looking at maybe horizontally or vertically, but we're looking at the theta from the origin, right? So this is actually going to be theta equals pi over 6, right? Because we're dividing both sides by 2. Same thing over here, dividing both sides by 2, and it's going to be 5 pi over 6. So just the way the unit circle works, you can use both of these, but it's general. In general, you're gonna want to use the smaller one, right? Because we know that this measurement is what it means by theta equals pi over 6, right? This angle right here on the unit circle. But just the way it works, we can use either side, right? Because this is a kind of symmetrical function, so we can use either side, so it doesn't really matter. So the integral we're going to be using to isolate both of them is going to be taking the integral of the actual lemniscate, so this area right here, and then taking the integral of the circle, and then we're going to be subtracting those two, right? So the area of the entire lemniscate minus the area of the circle, which is going to be just, you know, r equals 2, and the lemniscate, which is going to be r squared equals 8 cosine 2 theta, just to sort of reinforce the idea. So we'll take the integral of the lemniscate first, because we have to subtract the area of the circle from it. So what we can do is, well, I'll write up here the area, how to find the area of a polar equation or a polar graph. It'll be 1/2 the integral of alpha to beta, which are just 2 points that we're going to be looking at. In this case, it'll be pi over 6 to 0, or pi over 6 to negative pi over 6 of the equation. So f of theta, which is just r, right? R is a function of theta. All right, you input a theta and you get an r. So we can do from 0 to pi over 6, right? So that's going to be from this line, or we can look on this side, this line to theta pi over 6. But we're going to need to multiply it by 2, because that only gets the top half. But if we multiply by 2, we're going to get the bottom half too, right? That would only, let me use a different color for this to show this. That would only give us this, but we also need to get this, and that's, we can do that by multiplying by 2. Right? So we can take our function of the lemniscate, which is 8 cosine 2 theta, and under normal circumstances, well, it is squared, but remember that the r is squared. So when you square root by both sides to isolate the r to get just solely a function of f of theta, the square is going to cross out anyway, so we don't actually need that. All right, d theta, and this is function of one side of the lemniscate. One side of, we can just call it lem, just for short, right? So let me see if I can I just, nope, deletes the whole thing. Okay, it's fine. We'll just write it a little bit down. Minus, so now we have the area of the lemniscate. Now we have to take the area of just that angle of the r equals 2. So it's going to be 1/2 area of 0 to pi over 6. We can do the same thing as the last one over here, except we are going to be multiplying it by 2 again, right? So from 0 to pi over 6, we're going to be getting this top area right here. Oh, well, for the last one, I should have highlighted this entire area, right, for this one. So this one, we're looking at, you know, this whole area. And for this one, which we're not really done with, we're going to be looking at only the area of the circle. So it would be this on this side. So we can isolate just this pink area, right? So the pink minus the green will give us just this portion of pink over here. And that's pretty much the consensus of these equations. So let's go back to the black and finish this off. So minus 2 1/2 from 0 to pi over 6. So we got that. And now we're going to get the r, which is going to be 2. And then we're going to square it, d theta. And that's the equation. Right? So I'm going to take this on my, well, actually, no, that's not complete. That is complete, but we have to remember that this is just of one side, right? And we also have the area of the other side. So we have to take this entire thing and multiply it by 2. So, I mean, at this point, you would pretty much get full credit. You would just take 1 point off. So it's not something to like worry about too much, but you know, you have to remember to multiply it by 2. So I'm going to use my T84 calculator, and so we're going to get 2, and then in parentheses we're going to do 4/3 for the integral 0 to pi divided by 6 of 8 times cosine 2 theta. And at this point I'm just doing this to make sure that if you guys do understand all the steps, that you get the same answer as me. And then it's going to be minus the integral of 0 to pi over 6, 0 to pi over 6 for d theta, right? And you are going to get 2.7. That is a 7 for sure. 2.3 no 2.73941. That's going to be the final answer. Let me just check with my original problem. Yeah, they're the same. Okay, so there you go. There is certainly a lot of steps. This is probably the most complicated indicated, find the area of the indicated region problem I got for polar graphs. So don't be mad at yourself if it's hard to grasp, because at first I spent a lot of time thinking about it, but I was able to get it, and I think this might be the only way to do it. Unless you probably could convert these polar equations into rectangular equations, which is like, you know, think of a rectangular equation like y equals x, right? That's a rectangular equation. Like, that would be probably y equals x minus 1 or whatever, however that works. But if you convert those to normal rectangular equations, then you might be able to take the integral of like this area right here. But I didn't bother because I think that might be a lot more work, and this is probably the easier way to do it. So I hope you found an understanding in it, and thanks for watching.